Every day we burn masses of alkanes to provide the energy we need to power our homes or drive our cars. And although alkanes are incredibly good fuels, their use has some serious consequences. In this video, we're going to look at what pollutants are formed when we burn alkanes, the effects they have on both our health and the environment, before going on to explore how their emissions can be reduced. So grab your Learn Pack and let's get started. When oxygen is in plentiful supply, complete combustion occurs, forming carbon dioxide and water as products. But unlike carbon monoxide, carbon dioxide isn't toxic. So what is it about carbon dioxide that makes it a pollutant? Well, carbon dioxide is a greenhouse gas and therefore contributes towards the greenhouse effect. But increasing concentrations of greenhouse gases in the atmosphere are enhancing the greenhouse effect, leading to global warming. Now, you've probably heard of all of these terms before, but people often use the terms greenhouse effect and global warming interchangeably as if they're the same thing, and they're not. So what exactly are greenhouse gases? How do they cause the greenhouse effect? And why does increasing the concentration of these gases lead to global warming? Well, to answer that, we first need to think about what happens to energy from the sun as it reaches the Earth. The sun emits short wavelength radiation which passes through the Earth's atmosphere. This radiation is absorbed by the Earth's surface, where some of it is then re-emitted as longer wave infrared radiation. Greenhouse gases in the atmosphere absorb some of this re-emitted infrared radiation, trapping it within the atmosphere. The remainder of the infrared radiation then escapes the atmosphere back out into space. And this process of trapping some of that infrared radiation in our atmosphere is what we call the greenhouse effect. And it's important to note that the greenhouse effect itself isn't necessarily a bad thing. Without it, the Earth would be far too cold for life to exist, as much of the heat provided by the sun would simply dissipate back out into space. The problem is that increasing the concentration of greenhouse gases in the atmosphere strengthens or enhances the greenhouse effect. This means that more of the infrared radiation re-emitted by the Earth is being absorbed by the atmosphere, and so less escapes back out into space. This causes the temperature of the atmosphere to increase, and it is this increase in atmospheric temperature that we call global warming. Global warming then results in potentially catastrophic events such as climate change and the melting of the polar ice caps. So we've already established that carbon dioxide is a greenhouse gas, which means that it's a gas that can somehow absorb infrared radiation. But what is it about molecules of carbon dioxide that mean they can do this, whereas other gases on our atmosphere, such as oxygen or nitrogen, can't? Well, carbon dioxide molecules are made up of one carbon atom covalently bonded to two oxygen atoms, and the bonds between these atoms are double bonds. These double covalent bonds are actually polar due to the difference in electronegativity between the carbon and oxygen atoms. The energy carried by infrared radiation can cause these bonds to vibrate, and this is because the carbon-oxygen double bonds vibrate at the same frequency as infrared radiation. And this means that the energy being carried by the infrared radiation is absorbed by carbon dioxide and temporarily stored in its vibrating bonds. So we know that complete combustion is the most efficient way to release energy from alkanes, but we now know that that brings significant environmental consequences with it due to the production of carbon dioxide gas. However, carbon dioxide isn't the only carbon-containing compound that can be produced during the combustion of alkanes. Sometimes when burning fuels there may be insufficient oxygen available, and this results in incomplete combustion occurring. During incomplete combustion, carbon monoxide gas and/or carbon particulates are formed. Carbon monoxide is a poisonous, colourless and odourless gas, and when we breathe it in, it enters our bloodstream and binds very strongly to the haemoglobin inside of our red blood cells. This reduces their oxygen carrying capability, preventing them from carrying oxygen around the body effectively. And without oxygen getting to the vital organs and tissues in your body, serious health problems begin to occur quite quickly. And at high enough concentrations, carbon monoxide poisoning can even be fatal. But carbon monoxide isn't the only pollutant associated with incomplete combustion. Unlike carbon monoxide, which is a gas, carbon particulates are small, solid particles of carbon, often referred to as soot. During incomplete combustion, these particles are released into the atmosphere where they contribute to air pollution, affecting both the environment and our own health. When breathed in, carbon particulates can irritate the tissues of your respiratory system, causing breathing problems and can worsen already existing conditions such as asthma. Carbon particulates also contribute towards global dimming. This is where the particulates in the atmosphere absorb and scatter sunlight, reducing the amount of light that reaches the Earth's surface. Now, the pollutants we've discussed so far have all been formed when the alkane fuels are burnt. But what happens if our alkane fuel somehow ends up not being combusted? Well, unburned hydrocarbons are exactly that. They're hydrocarbon fuel molecules that leave the engine without having combusted at all. And this can happen for a couple of different reasons. Either because the fuel and oxygen didn't mix perfectly inside of the engine, or because of the limited amount of time for the reaction to occur before the gases are expelled through the exhaust. Either way, some hydrocarbon molecules can pass through the engine without combusting and are subsequently released into the atmosphere. Now, the problem with this is that many unburned hydrocarbons are greenhouse gases. Like carbon dioxide, water vapour and methane, they also absorb infrared radiation that has been re-emitted by the Earth, enhancing the greenhouse effect and contributing towards global warming. Our next pollutant we need to look at is actually a little unusual, since it's actually formed from the air itself. The air around us contains roughly 78% nitrogen and 21% oxygen, and normally these two gases don't tend to react with each other. But inside an engine, temperatures can become extremely high. At these high temperatures, nitrogen-oxygen molecules from the air can react together to form nitrogen oxides, or NOx. The first nitrogen oxide formed is nitric oxide, or NO, and this is formed when molecules of nitrogen directly react with molecules of oxygen. The nitric oxide produced in this reaction can then further react with oxygen from the air to form nitrogen dioxide, or NO2. Now, it's worth learning these equations as they do sometimes come up in exams. They're not massively common questions, but they do have the potential to be an easy couple of marks if they happen to come up. Nitrogen dioxide itself is a toxic gas, and along with other nitrogen oxides can cause a number of other environmental and health problems. One such problem is that nitrogen oxides contribute towards acid rain. When nitrogen dioxide reacts with water and oxygen in the atmosphere, nitric acid can be formed. Now again, being asked to give this equation isn't a particularly common exam question, but it has come up in the past. As long as you know the chemical formula for nitric acid, it isn't too bad to have to work it out in an exam, but working it out and balancing it could take up valuable time. So you might just want to stick this on a flashcard and get it learnt. The nitric acid that is formed in this way can then fall as acid rain, which can damage plants, harm aquatic ecosystems and marine life, as well as damaging buildings. But nitrogen oxides can also cause respiratory problems because they can irritate the airways and damage lung tissues. So all around, not particularly great for us or indeed the environment. Now, there is one final source of pollution that you need to be aware of, but this one is also slightly different because it actually originates from an impurity inside of the fuel. Fossil fuels often contain sulphur impurities, and when the fuels containing these sulphur impurities are burned, the sulphur present in the fuels reacts with oxygen to form sulphur dioxide. Sulphur dioxide is a toxic gas, which is obviously an immediate problem, but one of the biggest environmental issues associated with it is acid rain. Like nitrogen oxides, sulphur dioxide can react with oxygen and water in the atmosphere to form acids. These acids then fall as acid rain, which, as we've just seen, can damage plants, aquatic ecosystems, and buildings. So now we've looked at a number of different pollutants and how it is they are formed, as well as the health and environmental problems they can cause. But knowing about these pollutants and why they're harmful is only half the story. If we're creating these pollutants by burning millions of tons of alkanes every single day, what are we actually doing to reduce their emission? Well, there are three methods or techniques that we need to look at for removing these different pollutants: catalytic converters, filtration, and flue-gas desulphurisation. Each one of these has a different role in helping to remove pollutants, so let's start at the top of the list with catalytic converters. Catalytic converters are devices fitted to the exhaust system of vehicles and are designed to remove carbon monoxide, nitrogen oxides, and unburned hydrocarbons from exhaust gases. As the name suggests, catalytic converters contain a metal catalyst, and the metal catalyst is coated onto a honeycomb structure in a thin layer. The metals used include platinum, palladium, or rhodium, and the honeycomb structure provides a large surface area for the exhaust gases to come into contact with the catalyst. This means more pollutant molecules can react at the same time, increasing the overall rate of reaction and therefore efficiency of the catalytic converter. The thin coating of the metal on the honeycomb structure also allows a large surface area to be achieved whilst only using a small amount of these expensive metals. Catalytic converters help to remove 3 of our gaseous pollutants, and rather cleverly, they do this in an interlinked way. One of the most important reactions that occurs in a catalytic converter is the removal of carbon monoxide. Carbon monoxide is a toxic gas, and the catalytic converter oxidizes it into carbon dioxide by reacting it with nitric oxide. Now, this is a really important equation to learn for 2 reasons. One, it often comes up in exams, but secondly, you'll notice it's actually doing 2 jobs at once. Not only is this reaction helping to remove carbon monoxide, but in doing so, it's also helping to remove nitrogen oxides. Nitrogen oxides are removed by reducing them with carbon monoxide, which itself is oxidized. This forms nitrogen and carbon dioxide. And note how this is conveniently the exact same equation as we just saw before. And this is why it's such an important equation to learn. It's a double whammy, as it's used to answer 2 different questions: how nitric oxide is removed from the exhaust gases, but also how carbon monoxide is removed from exhaust gases. Finally, catalytic converters also help to remove unburned hydrocarbons from exhaust gases. The unburned hydrocarbons either react with oxygen to form carbon dioxide and water, or they can react with nitrogen oxides to form carbon dioxide, water, and nitrogen gas. Another double whammy where we're actually dealing with 2 of our pollutants simultaneously. So catalytic converters don't prevent pollutants from forming in the first place, but they do help convert harmful pollutants found in exhaust gases into less harmful substances before they are released into the atmosphere. But note that catalytic converters aren't the complete superhero. They don't deal with carbon dioxide emissions, and in fact they actually increase the amount of carbon dioxide being emitted by converting some of our other pollutants into CO2. But what about our second method of removing pollutants? Well, AQA don't actually expect you to know about how carbon particulates are removed. However, I personally think it's worth a quick mention as they're actually relatively simple to deal with. Unlike the other pollutants we've looked at, carbon particulates are solids rather than gases. This means they can simply be filtered out from the waste gases as they pass through the exhaust. Simple, yet effective. And finally, our third method, flue-gas desulphurisation. Unlike carbon monoxide, nitrogen oxides, and unburned hydrocarbons, sulphur dioxide cannot be removed using a catalytic converter. So what do we do instead? Well, in large-scale industrial combustion, such as at power stations, the gases produced during combustion are released as flue gases. Before these gases are released into the atmosphere, they can be treated to remove sulphur dioxide in a process known as flue-gas desulphurisation. The flue gases are passed through a slurry containing a base such as calcium oxide or calcium carbonate. The acidic sulphur dioxide gas is neutralized by the base, removing it from the flue gases before they leave the power station. And in some systems, calcium oxide is coated onto a mesh, like the honeycomb structure in catalytic converters. This increases the surface area of the calcium oxide, allowing more sulphur dioxide molecules to come into contact with it at the same time, increasing the rate of reaction. Now, this doesn't solve the problem in your cars, which is why a lot of modern-day fuels have the sulphur impurities removed before being sold. So we've now seen how we can deal with the majority of the pollutants produced when we burn alkanes. But there's one pollutant we've not dealt with yet: carbon dioxide. And unfortunately, carbon dioxide is rather different from the other pollutants we've looked at. We don't have a practical solution for reducing or removing CO2 from exhaust gases. This means that the only real solution is to find alternative fuels and reduce our dependency on fossil fuels. Later on in the course, we'll look at biofuels as such an alternative fuel, but also how ultimately they're not carbon neutral, and so whilst reducing net carbon dioxide emissions, they don't truly solve the problem. Therefore, if we want to significantly reduce carbon dioxide emissions from energy production, we need to reduce our reliance on fuels that release carbon dioxide when they're burnt, and move towards lower carbon sources of energy. This leaves us with generating electricity using renewable resources, such as solar panels, wind farms, and hydroelectric dams, amongst other possibilities. We've now seen that burning alkanes as fuels produces a range of different pollutants, depending upon the conditions in which they're burned and what else is present in the fuel or even the air. We've seen the problems these pollutants can cause, from poisoning and respiratory problems to acid rain, global dimming, and global warming. And we've also explored the different ways we can reduce their emissions. But importantly, we've seen that there isn't one solution that works for every pollutant. Different pollutants require different approaches, and some are easier to implement than others. But combustion is just one reaction that alkanes can undergo. Now that we understand how alkanes burn and the problems associated with combustion, the next step is to explore how alkanes react with halogens to form halogenoalkanes through free radical substitution. The full topic playlist is on your screen now, so you can continue your journey through the chemistry of alkanes.